Welcome to lecture 41. In this lecture, I will be setting the stage to calculating the magnetic moment of the electron. Recall that in lecture 35, we discussed the setup for quantum electrodynamics, or QED for short. One of the precision tests for the theory of quantum electrodynamics is the so-called anomalous magnetic moment of the electron, also known as G-2. In this lecture, I will set the stage for calculating the anomalous magnetic moment by first calculating G, not G-2. In future lectures, I will then go on and discuss calculating quantum field theory effects that will give us an approximation to G-2. To set the stage, recall that we have a QED partition function given in equation 41.1 that contains the full field content. That is, it is a path integral over the gauge fields A, over the Dirac fermions psi and psi bar, and the ghosts C bar and C. The action is the sum over all the parts that contribute. That is the meta-Lagrangian, or the meta-action, that contains the meta fields, in our case the electrons, the gauge part of the action, the gauge fixing part of the action, which was necessary to be introduced in order to have a well-defined path integral, and the ghosts that were necessary to rewrite the determinant that arose as a part of the gauge fixing. These are the constituents of the action, and we've discussed those as part of lecture 35. For the electron, the meta fields are Dirac, and as such, we have an action for the Dirac fermions that's given the following expression. It's an integral over space time x, psi bar d slash plus m psi, where d is the covariant derivative that's built out of the gauge field A, and A slash just denotes the Dirac slash, meaning the contraction of the symbol together with a Euclidean gamma matrix. Recall that we want to have, we started from an action that was invariant under local U1 gauge transformations. These are transformations that take psi and send it to e to the I alpha of x psi, where alpha of x is an arbitrary function. We have discussed in lecture 35 that under this transformation, the action is invariant if the covariant derivative is given by the combination of the usual derivative plus I times the gauge field, and the gauge field transforms as a mu goes to a mu minus the derivative of this function alpha. In addition to the meta part of the action, we also have the gauge part that is invariant under this local gauge transformation if it is built out of the field strength tensor F mu nu, which is just the antisymmetric derivative of the gauge fields. Note that I have included a prefactor here, and there's a parameter E that will turn out to be the strength of the coupling. At this point, it is an arbitrary constant. Since the normalization of the gauge field is also arbitrary so far because it drops out from the path integral, we can change the normalization of the gauge field by, for instance, multiplying all occurrences of A by a constant, such as A goes to E times A. If we do this, then the sum of the matter and gauge part of the action are written in the following form. So we have psi bar d slash plus I e A slash psi, and plus 1/4 F mu F mu instead of 1/4 E squared F mu F mu. In the following, we will use this normalization, which is pretty standard for perturbative calculation in QED, as our base. Recall that we calculated the Hamiltonian for a Dirac fermion back in lecture 32. We found that the Hamiltonian is given as the integral over space times psi bar minus I gamma I partial I plus m psi. And I just want to draw to your attention to the fact that the gamma i's here are Minkowski gamma matrices. We can change notation such that we have Euclidean gamma matrices throughout. And for the spatial parts of the Minkowski matrices, this just amounts to replacing gamma I by by minus I gamma E. If we do this, then we find that using the Euclidean gamma matrices gamma E, we have that the Hamiltonian is given by this expression. It is straightforward to see that this Hamiltonian here is effectively part of the meta part of the action, because we have psi bar d slash psi. That's also part of our action here, psi bar d slash psi. So it's straightforward how to correct for further contributions in the Hamiltonian. This Hamiltonian that I had on the previous stage that we derived in lecture 32 was for free Dirac fermion. If we consider another coupling of the fermion and the gauge field, similar to the meta part of the action, we find that the corresponding contribution to the Hamiltonian must be given by the following form, i.e. integral over space psi bar a slash psi. We can rewrite this by pulling out or writing the a slash in the form gamma mu a mu, such that it becomes apparent that this is a contribution that involves the fields of the fermions and the gauge field. We can, for instance, consider a certain gauge fixing condition, such as the temporal axial gauge, where we set the zero component of the gauge field to 0. So if we do this, the Hamiltonian contribution in this gauge becomes IE d3x psi bar gamma I AI psi. So having this Hamiltonian contribution, we want to rewrite this now in a limit where a is small. If a is small, then the fermions in QED fulfill the Dirac equation, because any contribution that comes from the coupling of gauge fields and photons would be an additional contribution of order A, but we take the gauge field A to be small in amplitude. So we have the Dirac equation here. We can therefore switch to Euclidean matrices again and use, in particular, concentrate on time-independent fields. So the time derivative of this equation just drops out. So then this equation here just becomes m psi is minus gamma e partial I psi. We can take the Hermitian conjugate of this equation and multiply by gamma naught, such that we find on the left-hand side just m psi bar, and then the right-hand side, if we use the hermiticity of the Euclidean gamma matrices, we find that this is di psi bar gamma IE. Now that we have these two equations, we can multiply the first equation by psi bar gamma j from the left and gamma j psi from the right for the other equation. So then these two equations are now listed in equation 41.16. We realize that on the left-hand side, we have the same expression. So if we sum this up and divide by 2m, we find the so-called Gordon identity that relates psi bar gamma j psi to products of gamma matrices and a derivative. We can further simplify this expression by separating or writing the product of two gamma matrices as an anticommutator and a commutator, and introducing the notation sigma ij for the following combination of anticommutators. We can write this as minus I sigma ij, and using the fact that the Euclidean gamma matrices fulfill the Clifford algebra such that the anticommutator is just twice the Kronecker delta, we find that the other contribution is just delta ij. Now, if we substitute this expression into the Gordon identity, then the delta function is the same left and right. So we'll get one contribution that's di psi bar psi minus psi bar di psi. And then we have the anticommutator sigma ij, but this contribution will have a different sign because here we have the ordering ij, and here we have JI, so we get a plus for the contribution proportional to the anticommutator. If we do this, then we get for the coordinate identity the following result, where we now have a single derivative acting on the combination of psi bar, sigma ij psi. Using this coordinate identity in the Hamiltonian, we then find that the Hamiltonian has two parts. There's one part that is given by this combination of derivatives in the first part and the aj. And then there's a second part that then has this total derivative of this expression times the gauge field. For now, I'm not interested in this first part here. So let me just concentrate on the second part here and then use partial integration to rewrite this as a derivative of the whole expression, which vanishes because of Gauss's law, minus something where we have this expression and the derivative acting on aj, which is nothing else but a contribution of the field strength tensor Fij, because sigma ij is antisymmetric, so these derivatives can be made antisymmetric as well. So you get a contribution that is just the field strength tensor Fij. I will call this second contribution spin-orbit interaction, as we shall see in a moment. We can then consider the situation where we evaluate this contribution in a constant external magnetic field. So basically I take Fij to have only one non-vanishing component, let it be the component 1, 2. And I want this component to be constant, equal to a constant magnetic field in the 3 directions. So I call this B3. In this case, then I can write the contribution as minus E over 2m, which I write as mu b for the Bohr magneton, times the integral over space, psi bar, sigma 1, 2 psi, times B3. Note there's a factor of 2 that's coming from the summation Einstein sum convention, because we are summing over both I and j in the previous slide. Now we can inspect this particular combination, the commutator of the Euclidean gamma matrices, gamma 1, gamma 2. And if we plug in, for instance, the Dirac representation for these matrices, we find that this commutator is given as minus, and this is a block diagonal notation where we have sigma 3 for the third Pauli matrix, and this is a 2 by 2 zero matrix, another 2 by 2 zero matrix, and again the third Pauli matrix in the lower block of the matrix. So this 4 by 4 matrix is essentially block diagonal, and as such it has a particular property, namely it's proportional to sigma 3. Sigma 3 is essentially part of the spin operator. So for a spin 1/2 particle, the spin operator S3 is given by this particular matrix with a prefactor of 1/2, so that the operator has the correct eigenvalue for a spin 1/2 particle. So if we use the spin operator to rewrite the Hamiltonian contribution, we find that the spin orbit contribution is given as twice the Bohr magneton, the integral over space, psi bar psi times the product of the spin operator and the magnetic field. So basically we have the usual form of a spin orbit interaction, hence the name spin orbit interaction here. It is proportional to the spin orbit coupling and corresponds to the coupling of spin to the magnetic field. The only, if you want, a non-trivial piece is the numerical factor of 2 here, which is a consequence of the fact that the Dirac particle here is a spin 1/2 fermion. So we have this factor 2, and that is the non-trivial factor. And this factor can in principle be different from 2, then we call it G, but the leading order of the G factor is just this value 2 that we just derived in equation 41.26. Note that the treatment that we've done in this lecture is relativistic. It contains fermions, but it doesn't really contain any true quantum field theory effects. Some people call this do not call this classical because it contains fermions or because it's relativistic. There is some sort of sense to it, but in our at least setup, it does not correspond to a truly quantum field theory treatment. So in that sense, it's classical. Therefore, the result G is 2 is a classical approximation for the actual G factor. And we can look for deviations from the result G is 2. This is called anomalous contribution to the magnetic moment, although there is no actual anomaly at play here. It is just different from 2, and for some reason it's called anomalous, even though in the quantum field theory context, anomaly typically has a different meaning, but this is sort of, for historical reasons, called anomalous contribution. In the next lectures, we'll set up quantum field theory treatments to approximate the quantum field theory result for G-2. And that concludes the present lecture.